Hello, students. Last section of chapter 13, 13.5, volume and mass. Now, again, these are kind of combined. Um, they do connect perhaps a little bit better, but they are kind of also connected to length. So we oftentimes use length to get us area, and then from there we sometimes convert area to volume by adding length in a third dimension. Now, if you think about it, then we could measure volume instead of saying that milk is measured in the gallon, we could say how many cubic inches is it. So just understand, we'll see that reference, cubic inches, and we just need to understand all it means is it's a three-dimensional measurement. Sometimes we have other measurements that represent three-dimensional measurements, but again, they're maybe for a little bit more ease of use, or they're just because we've done it that way for so long. So when we start looking at three-dimensional shapes, we can break the shape down into things like surface area, where we're counting squares, like the front part of the square, and then the side parts, the top parts. We're counting all the surfaces. But we could also count volume, which would be measuring cubes. So here, just 1, 2, 3, and 4 cubes. 4 cubic units, which again, if these were 1 inch by 1 inch, that would be 4 cubic inches. Uh, it can also be abbreviated as cubic inches. Just so you're understanding, that's something that could also be there. And up here, when we had 18 square inches, we would have something that looks like this, or 18 square inches. All right, let's move on. What do we have for Common Core? Well, Common Core, grade 5. So 5th grade, we're finding volume of rectangular prisms with whole number side lengths, and we just packing those with unit cubes. The volume would be the same as found by multiplying edge lengths, multiplying by the height of the area of the base. So notice the height by the area of the base gives us the idea, hey, we may be using something similar to what we did with surface area. So let's take a look. If we are truly going to go ahead and measure the volume of something, we would be counting little cubes. And so what you can do is think of cubes as being a three-dimensional object. We can count how many cubes on one side and how many going backwards. And again, if I did 8 times 4, 8 times 4 is 32, but that would be square inches. And that would kind of represent like how much area is on the top and the bottom. Okay. But when I bring in a third dimension of height, now each of those cubes kind of has a thickness. And so what I do is I kind of take layers of that thickness. So this top layer all the way across would be 32 square inches on top by 1 inch thick. And then I would stack that 5 total times. So I would say 5 times 32 to get me 150, 160 cubic inches if we were doing that. Okay, we can see that here, 160 cubic units. So overall, we do have that volume is the length times the width times the height. Now, just be aware, if we're talking about a right rectangular prism, length times width is the area of the base. So if you look back at that Common Core statement, it talks about the area of the base times the height. That's what it's referring to. Okay. All right. Well, let's move on. How do we convert metric measures of volume? Well, here's a fantastic thing. I hope you still remember King Henry's Dear Mum drinks chocolate milk. King Henry's Dear Mum drinks chocolate milk. And the reason why that's important is that is how we move between things that have a base unit of a meter. So if we had, they have a conversion rate here. And you'll notice that if they're going to do cubes, they repeat it 3 times. That's perfectly fine. What I want you to see is that you can still get there using what we had here. It's just if we're in 1 dimension, 2 dimensions, or 3 dimensions. So if we're doing 1 dimension, then it is 1 step. Actually, I should say one per step. One per step. If you're doing 2 dimensions, then it's 2 per step. And 3 dimensions, you can imagine, is 3 per step. So what does that say? If I had 5 centimeters and I want to know how many millimeters that is, you come up to the table, find centimeters. How far do I have to move? I move 1 to the right, but centimeters is 1 dimensional, so 1 per step. So I move 1 decimal place per step. Okay. Now what's the difference? What's the difference if this was centimeters squared? Squared means 2-dimensional. 2-dimensional is 2 per step. So I would move 2 decimal places for each step I had to take. And likewise, if I was doing something that we're going to do in this unit, it would be 3-dimensional. So I might have cubic units. Then even though I'm still making a step of 1 step, I move 3 because it's 3 per step. And that becomes 5,000 cubic millimeters. So cubic centimeters becomes cubic millimeters, but it's 3 per step. You can see them trying to do that here. I want to generalize it so that you don't have to be thinking, what do I do next? Also, if you had 5 cubic centimeters, and you want to use the other system we have done, my recommendation remains put in the units that you know, put parentheses, and then say it's 3-dimensional, so I need to put a cube on here. That way you have centimeters on the bottom, but it's being cubed, so those do eliminate with the cubic centimeters. It leaves you at the end with millimeters cubed, and 10 cubed turns out to be 1,000, and 1,000 is 3 decimal places, which is exactly what we said. 1 step for 1-dimensional, 2 for 2-dimensional, 3 for 3-dimensional. So this becomes, again, 5,000 cubic millimeters. All right. They say compute all of those. So here's, this is a good one. So 5 meters, 5 cubic meters. Let's see here. So 5 cubic meters, and we want to turn it into centimeters cubed. Whoopity-doo. So you got 2 ways to do it. One is kind of draw it all the way out. The other is King Henry's Dear Mom drinks chocolate milk. King Henry's Dear Mom drinks chocolate milk. And I would say from meters to centimeters. So that's 1, that's 2. So it's 2 steps, but remember, this is 3-dimensional, so it's 3 per step. So that's 3, and 3 more, that's 6. So start with the number 5, and then move it 6 places. 1, 2, 3, 4, 5, 6. Put zeros everywhere we need them, and so this becomes 5 million cubic centimeters. There you go. Woo! All right. Let's hear what else. I mentioned that the King Henry's Dear Mother Drinks Chocolate Milk is fantastic, but every time you move to a different system, all you do is change the base unit. So when we move to something that's now measuring liters, now we're counting tens of liters, hundreds of liters, and so forth. And so by definition, a liter is the capacity of a cubic deciliter. A cubic decimeter, sorry, cubic decimeter. So there you go. 1 liter is 1 decimeter cubed. Okay. So what does that really mean? Well, a decimeter cube is not one that we tend to use. We tend to use cubic centimeters. That would be 1 step down. 1 step down is 3 because it's 3 per every step. So 1 liter is actually 1,000 cubic centimeters. That's probably the one that would be a little bit easier to work with. But 1 liter, if we think of King Henry's Dear Mom drinks chocolate milk, we would put M in here for mom, but we're going to do liters now. Just put liters as your base. And if I want to go down from liters, I could move from liters to 1, 2, 3 to be at milliliters. So as it turns out, 1,000 milliliters is the same as 1,000 cubic centimeters. which means that 1 cubic centimeter is 1 milliliter. There we go. There is our relationship. And so anyway, that's metric system. Gotta love that, right? 1 cubic centimeter, 1 milliliter. That's quick and easy. Not the same in the United States system, just so we're all on the same page. It's not the same. 1 square inch is not the same as some other fun measuring device. It's not. Or 1 cubic inch is not the same. So if you're moving between liters and milliliters, just understand those are not being cubed. Okay. Milliliters is a measurement of something that's already cubed. So we can just count them and move just up and down. But if you're going from, let's say here, this one's cubic meters, I would say this last one's probably the most challenging. So let me get a little bit of white space and I'll kind of demonstrate that one just to illustrate what we're talking about. So here we go. If we have 3 cubic meters, I want to end with liters. Well, I don't know how to do that, but I do know that 1 cubic centimeter is the same as 1 milliliter. Okay, so let's go through and do our calculations. 1 meter is 100 centimeters. I'm going to put cubed on here because, again, it's cubed, meters cubed. Okay, now what's going to happen there? The meters cubed are going to go away. I'm left with centimeters cubed. What do? 1 centimeter cubed on the bottom because I want to get rid of it. 1 milliliter on the top. Cubic centimeters are now gone. And then let's see here, milliliters to liters. You can either put in the conversion or you can just move the decimal at the end. So that's completely up to you. So 3 cubic meters right here becomes 3 of those. So 2, 4, 6. So I have 3, 1, 2, 3, 4, 5, 6 milliliters. But now milliliters, King Henry's Dear Mom drinks chocolate milk. Milliliters becomes liters. From milliliters, I go 1, 2, 3 to get back to liters. And okay, got it. So I move back 3 decimal places, and that becomes 3,000 liters. And that is how you can do that kind of a problem. So 1 step at a time. They used 1 cubic meter is this many DMs and DMs to liters. Again, I'm not advocating that you memorize all of the options. Just think of one of them. If we are using the English system, oh my gosh, you're going to think it looks a little bit crazy, but I think once you get used to it, you'll be okay. So for like this first one, if you said 45 cubic yards, put it over 1, put in your conversion, which is 1 yard is 3 feet, put in the parentheses, match because I'm doing 3 dimensions, make it a 3. So cubed yards goes away. That means I end with cubic feet, but now I just do 4 in my calculator, 45 times 3, and then don't forget to the 3rd power. So it's really 45 times 27. And I think you get something like this, 1,250 cubic feet. All right. So again, all of these are very, very similar. Notice there are a few that I would say just have them jotted down on your note page, but I will give them to you on the test. If I ask you to do something with gallons, I will put this conversion on the test. I will say 1 gallon is 231 cubic inches. I will promise you, I will tell you that. You do not have to make that up or memorize it. Okay, I will tell you that one. In terms of the rest, cubic feet, cubic yards, cubic inches, those you need to know because you know yards to feet, feet to inches, inches to miles, all of those. Yes, you need to know that. Okay. Let's see here. What else do we have? Volumes. Volumes of prisms and cylinders. Well, again, if I have a rectangular solid, it is a prism. Therefore, the volume is base times height. And remember at the beginning of the section, they said, hey, why don't we do something different than they said it's the length times the width. So they said the volume is the length times the width times the height. Just remember, length times width is the area of the base. Okay. And what I want you to do, I want you to think about this. What we're really doing is we're taking one like one thing of thickness and we're stacking it on top of each other. So that's why we're multiplying by h. We're saying how many of these thickness layers of level 1 do we have going all the way up? Okay. Now, you might have been saying, wait, Scott, I remember when we did these shapes earlier, we had these oblique cones or oblique cylinders that are shifted off to the side. But there's a really cool thing by a mathematician named Cavalieri. And Cavalieri's principle said this: the amount of volume, think about Jello, right? If I push it to one side, sure, the Jello kind of nudged to one side. So instead of looking straight up, now it's curved, but the other side is curved as well. And it has the exact same amount of volume. So he took this as kind of slices, and he showed how if you add all the slices up, we get the same thing, which says it doesn't matter if it's shifted or straight up and down, it's the same. Now, again, the height from the top to the bottom would have to be the same to do this. If you twist it so the height from top to bottom is not the same, then of course that is not the same shape. So two solids with each base in the same plane have equal volumes if with a base in the same plane have equal volumes if every plane parallel to the bases intersects solids in cross sections of equal area. So again, if you slice across, you get exactly the same area, then it's going to work just fine. All right. So again, here's an example of this, although I don't think it's the best example. It's an interesting example because one's a right triangle prism, the other one is a square prism, but it gets you the same idea that the cross-sectional areas have to be exactly the same from top to bottom, and these are exactly the same, so therefore their areas would be the same. You just have to compute one of them. And there's a little interesting information. If you're Italian, there you go. Another Italian mathematician coming in, Cavalieri. All right, so next up. So again, when you see these other shapes, don't think of it as anything different. They're all the same. The volume is the base times the height. And that is for what? That is for prisms and cylinders. So nothing different. When it's oblique, you don't care because you can still find the area of the base, and then the height still has to be that height, which is that right angle altitude. So don't change your thinking about these just because they may look a little bit different. Love it. Okay, volumes of pyramids and cones. Um, yeah, this is kind of a very interesting one. We will I'll do my best to make sure we can demonstrate this in class. So what we're going to do is we are going to take one of these pyramids and pour it into the right prism, and we'll come up with a nice little relationship. How many of these right pyramids does it take to make a right prism? So if I pour this one in here and I repeat, it looks like it might take at least two of them. Turns out it doesn't take two of them. It takes exactly three, as long as the base has to be exactly the same as the base, and the height has to be exactly the same as the height. So that's what it takes. And so basically, three right pyramids make one right prism. So if you know that, then the volume, which used to be base times height for the prism, for the pyramid and the cone becomes 1/3 base times height. I know. That's pretty cool. If you want to see an idea, this is their visual idea of why that is the case. They are taking this with a cube, and all that means is that the sides are the same, which means if the sides are the same, that the altitudes are the same for all of these. And they're breaking the cube down into three pyramids. And guess what? The pyramids have equal volumes because they have the same bases and the heights are the same. Therefore, we can kind of think of breaking down that beautiful prism into three pyramids. Here is a volume of cone, volume of cylinder from a school book page, taking some frosting, putting it in a pastry bag so you can kind of make a fun decoration on top of it. And they say, well, how much can I put in there? if they are the same height and they have the same base dimensions, we're in trouble. However, what's interesting is this bag is laid flat. I don't know. I would question this. If it was 4 inches across and it was laid flat, when it was filled, there's no way it would have the same diameter there. So I think that's a little bit misleading. But again, what can you do? What can you do? We can't win them all. All right. Yeah, I'm okay with that. They said they're going to unfold it into a net. To me, that's not as critical. So in terms of these, your goal is to find the volume. If you're trying to find volumes, why don't I go through and I'll do at least one of them. Maybe I'll do the one for the cone. So what I would do is I would find the volume of the cone. I know it's 1/3 the area of the base times the height. The height is listed as h, but the base I can figure out because the radius is 6. So I know this is 1/3 times pi times the radius squared. And now for the height. The height, I'm going to come off to the side. I'm going to draw a right triangle because I know this is 6 and this is 10 and h is here. Good old 13.3 with the Pythagorean theorem. And we have 6 squared plus h squared equals 10 squared. And that gives me 36 plus h squared equals 100. H squared equals 64. Aha, h equals 8. So now I know my height is h, so put that in times 8. Well, let's see here. 1/3 of 36 is like dividing by 3. That's 12. So I end up with 96 pi centimeters cubed. Bada bing. Woohoo! They got the same thing we did. I love it when that happens. All right. They got a net here. Again, if you have the net, sometimes the net is helpful. And I said it's a challenge at times to find the height, but if you know some other pieces at times, you can. So if I know from here out to the edge, that would be 5, right? And then the slant height, depending on the triangle, I need to know something about the triangle. In this case, it's equilateral. So that means the height out here would be 5 square root of 3. Okay, because this side here would be 5. 5 square root of 3 over 2. And again, that's because this length right here would be half. So 1/2. Yeah, because it's a 1 to root 3 to 2 ratio. So I'm just using that piece from chapter 13.3. And so if the big side was 5, so if you take this down and you say, okay, my big side is 5, it means I had to divide by 2 and then multiply by 5. So you divide by 2 and multiply by 5, you get 5/2 for the middle one, for the small one, and then 5 root 3 over 2 for the middle one. So that's why I'm choosing that one here for the height. Now, once you have that piece right there, that's your slant height. When you bring it back together to find the actual height, you're going to have to come right down the middle here. So there you go. Woo woo. All right, last piece. Volume of a sphere. The volume of a sphere is 4/3 pi r cubed. Right? So there we are. Now remember the surface, this is the volume. The surface area was 4 pi r squared. And if you were taking a class in calculus, you could actually say how fast is the volume changing with respect to the radius. And this would be known as the derivative, which is a fancy way of just saying how fast is something changing. And the way we do that is the exponent here comes down. So we get 4/3 times 3 times pi r, and this goes down by 1. So we get 4/3 times 3 times pi r squared. The 3's go away, and we actually get 4 pi r squared. The volume of a shape is changing based on the surface area. So if the surface area has a little bit of a change, in this case, based on the radius, that's how the surface area and the volume connect. So again, if you're interested, there are higher level math concepts at play. Do we care about that in this class? No. But I will show you a cool way, at least I think it's a super cool way to show why is this the same formulaic-wise, if you will. So when you look at this, we're going to do something in class that shows you where this comes from. And we'll probably do it by taking some of those pieces and kind of filling them up with water, if you will. All right. So that takes care of that piece. Whew. Let's see here. Comparing volume of similar figures. Let's see here. Scale factor of 3. We're getting back to the ideas that we talked about in the beginning. If you increase one side by a factor of 3, it's 3 times as big. If you increase each side of a figure, two-dimensional figure, by 3, the area now becomes 3 squared times. And if you increase it by a factor of 3 for a three-dimensional shape where every dimension is 3 times bigger, your overall volume becomes your original volume, which would have been 16 times 3 because you tripled every dimension. So we're going to cube it. And there it is. So really you get 16 times 27 is what we really end up with here. So to me, and again, that does come out right down here to 432. They did it kind of the long way, but once you start to see these connections, it is magical how they're related. So if the scale factor of two similar figures is k, the ratio of their areas or surface areas is k squared, and the ratio of their volumes is k cubed. Basically, every unit that you use, you multiply it by itself however many times you have for that dimension. All right, there's a couple other example problems. I'm not going to go through all of those, and because I want to get into the last piece, which is mass. For most of you, if you were to say how much, how much do you weigh, you would say how many pounds. We have a little bit of an issue because in weight actually is a force exerted by gravitational pull, whereas mass is a quantity that can be kind of universal. So if you think about like you go to space, you still have some mass, but your body doesn't weigh anything because there's no gravitational pull. If you are on the moon, I think the moon is like 1/6 of Earth's gravity. So you see people kind of looks like they're hopping, and that's because they don't have to push very hard to go against the force of gravity on the moon, because again, it's much smaller. So I want to separate those. One is mass, the other is weight. For the English system, we tend to say everything is measured in kind of weight. But mass, the metric system has a unit for mass, which is a gram. And again, King Henry's Dear Mum drinks chocolate milk. They replace meter with gram, kilograms, milligrams. All of those are going to be utilized here. For the American system, we use pounds. And pounds, what's great is that their 1 pound is 16 ounces. And then 2,000 pounds, we call 1 ton. Okay. What else do we have? Pounds we often refer to as lb or lowercase lb. And that actually goes back to some of those star signs, like the star sign. If you know about this one, Libra is balancing them out on a scale or a measurement. So we take it from, yeah, I know, isn't that great? We take it from their LB. I think that's kind of cool. But again, we have to memorize some crazy stuff in our system. In the metric system, you do not. They just use gram as the base, and then you go up. Kilo, hecto, deca, gram, deci, centi, milli. Now, they do have a metric ton. A metric ton is just 1,000 kilograms. So again, really nice when they go up. They're just like, yeah, it's 1,000 of those. It's 1,000 of those. We don't have to have all these kind of crazy units. And lastly, relationship among metric units of volume, mass, and capacity. So we've talked about 1 cubic centimeter, which we know is 1 milliliter of water. That was from volume. That has the same amount of mass when we're talking about water as 1 gram. Okay. So that's a really nice conversion in the metric system. That is not the way it works in the English system. What that means is 1 cubic centimeter, which we could say one liter, then 1 liter is 1 decimeter. 1 liter of water weighs 1 kilogram. Basically, take each of these and multiply by 1,000. That's the metric system. Okay. Let's see here. I guess I should, that's really strange. Thought they would have it in here for you. I'm going to bring this up because I think it's really, really important. Okay. So when you buy a bottle of water and the bottle of water says 16.9 fluid ounces, that is a measure of volume, not mass. I know it says ounces, but in America we use fluid ounces and we also use weight ounces. Well, 16.9 fluid ounces is about 500 milliliters of water. Okay, that's what it is, 500 milliliters of water. Well, milliliters of water means 500 grams, because 1 milliliter is a gram. So I have 500 grams. That looks horrible. There we go. Is 500 grams of water. Remember, 1 milliliter is 1 cubic centimeter is the same as 1 gram. So 500 grams of water, which becomes half of 1 kilogram. So then now in order to kind of get it back into American measurements, kilograms is the metric system. The metric system is not the same in terms of mass. So if you come over here, let's do this. 1 kilogram is 1,000 grams, but if I say to pounds, 1 kilogram is worth 2.2046 pounds. So let me write that down over here. 1 kilogram equals 2.2046 pounds, approximately, right? We're rounding at this stage because it's not exact. So you sometimes will see 2.205, 2.2046. I'm going to use 2.2046. Again, I'll write that one on the test. So what I do is to finish this one off is I come back and I say, okay, so I need to multiply this by 1 kilogram is 2.2046 pounds. Kilograms go away. I take half of this and I get 1.1023 pounds. So here's what's great. 16.9 fluid ounces of water. That amount of water weighs about 1.1 pounds of water. So I'm saying there's not a quick measurement back and forth in the English. For the rest of the world, they would say 500 milliliters. They already know that that's measuring volume, and they can very quickly turn that into mass because well, honestly, they could say 1 liter is the same as 1 kilogram. I have half of a liter, so I have half of a kilogram. They're done. But for us, we have to go through a lot more steps to kind of convert back and forth. And so anyway, I wanted to show that just so we're really clear. There's a big difference between that. Now remember, why am I showing this? One last piece. This is pounds. Okay. But if I had 1.1023 pounds, and I know that 1 pound LB is the same as 16 ounces, not 16 fluid ounces, right? When I multiply these together, 16 fluid ounces, let me grab my calculator, 16.9 gives me, doop, 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 doop. Let me see here. 16 times 1.1023. Oh, you're gonna love this. At least you're gonna love the fact that we're here in this country because we get the chance to really work our brains. 17.6368 ounces. So again, 16.9 fluid ounces becomes a little bit over 1 pound, which means it's a little bit over 17 and a half ounces. There's a difference between ounces and fluid ounces. So make sure when you're answering questions on the exam or in your homework that if it says fluid ounces, you use fluid ounces. If it says ounces, make sure you use ounces. And I believe that gets us into the homework, which means we are wrapped up for chapter 13. I hope this was very helpful for you. Please take a chance. Let me know if you have questions. I'll post additional videos as necessary. All right, off you go.